Okay, hi guys. This is my video tutorial on Boolean Algebra. In this tutorial, I'll only be going over the basics. However, it does get much harder than this. However, you really need to have what I'm about to tell you down before you move on. Now, Boolean Algebra is sort of like a logical type of math. You'll use this a lot when dealing with computer science, both the software and hardware side of computers. Hardware wise, it helps a lot with schematics. I used to use this a lot when I was building Minecraft computers. And why this is useful is really hard to explain too unless you know a lot about it. So I'm just going to dive right in. The first thing you need to know is what is a Boolean. Whenever you're dealing with Boolean algebra, every time you see a variable, it is either true or false, and that is all. There is no other possible answer that it could be. Now, when you see this 1 and 0, you're gonna think in terms of binary, because if you ever, or maybe you're in a programming class right now, any of those type of classes, they're probably going to go over what a binary value is. A binary is either a 1 or a 0. The word bi, because it's a value with two states. All Booleans are binary, but not all binary are Booleans, because it has the same relationship as a square and a rectangle. Okay, this is AND logic. The way AND logic works is, in order for the result over here to be true, the first value and the second value must be true in order for the result to be true. Up here, these are just all the symbols that you'll see people use. This is used a lot in like articles and stuff. This is just Shift 6 on your keyboard. This is just AND written out in capital letters, and then any type of multiplication sign means AND as well. Now, AND works is really interesting the way it works when you have groups of variables that are all bound by AND operators. In order for the result to be true, in groups like this, every single variable has to be true, which means that if you have a 0, like this over here, either the groups or just one variable, the result of the entire equation equals 0. If you have the opposite and you have 1 or a true value in any type of equation, the 1 becomes insignificant. It doesn't matter in the result. See, as you can see, I have A and 1. The result is just A. And then over here, it's almost like you're just cutting them out. They're not even important. But however, it is important that you take that out of the result, because you need to simplify it as much as possible. Okay, so these are just examples. Right here you have A and A. Now, if I were to have a 0 in A and 0 over here, it would make the entire equation 0, because it would be B and 0. And because of that, well, and if you look at the other way, if I had 1 right here and a 1 right here, this would be true, and then it would just end up being whatever B is. Because of that, not the entire equation, but this part right here is redundant. This is insignificant, and because of that, the result is just A and B. Now over here, I just talked about this. The 1 becomes unnecessary, and you have A and X. Now down here, whenever in Boolean logic, if you have the same operators, the equation has all the same operators, it doesn't matter where your parentheses are, or if you have this crazy inception of parentheses. It doesn't matter if you flip the numbers around. All commutative and associative properties apply when dealing with equations that all have the same operators. So right here, the parentheses don't even matter, and again you have this 0, which makes the entire equation 0. Down here, same thing again, even though you have a lot more, like these 1s don't even matter, but then again you have this 0 at the end, which equals 0. Now unfortunately the world won't highlight all the exact values like I have. See, the 0 really sticks out because of the red, and because of that you're easily able to tell that the result is 0. Now this is OR logic. The way OR logic works is, in order for the result to be true, both variables, not both variables, but one or the other has to be true in order for the result to be true. Now you only need one. However, since this one definitely has 1, the result equals true. And that part of OR logic is inclusive. It includes the idea that both A and B can be true and the result would be true. Oh, again, these are just the symbols that you can use for OR logic. This is just plus symbol, and over here is just a capital letter V. Okay, when dealing with groups of OR logic, if you have a 1 in the equation and it's all OR logic, the final result is always true. And the reason for that is because if I were to do this one at a time, A and B, we don't know what that is. B and C, we don't know what that is. C and 1, well, that would just equal true, because C can either be 0 or 1, and that would still make the equation true. So then we would have 1 and B, and we would just, same reason again, it would be true and then true. Because of that, the final result is just true. Now with 0, this works the same way as a true value would in AND logic. The 0 just becomes insignificant. It doesn't matter. That's why, if you look at the results, it's just the same thing with the 0 taken out. Okay, over here, this is just OR practice. Again, you have this 1. The entire equation is equivalent to 1. Now, again, these parentheses don't matter because they're all OR operators. And because of that, the A would be redundant. You have it 2 different places, A or B or C. Now, number 3 is the same thing as the result up here. If I said this was the simplified up here, you can draw the conclusion that this is obviously just the simplest form right here, because this expression cannot be simplified. There's nothing you can do with it. Down here, this equation is longer, but again you have the 1 on the end, so the entire equation is 1. Okay, this is not logic. And not logic is even easier. Well, for me it is. I would say it's even easier than both AND or logic. All it does is it inverts the value. So the result is always the opposite of the variable that it's used with. For an example, if you saw this in equation, it would look like this. If you saw A, the inverse of A, this is what the equation would look like for the results. Now over here, you can have not logic over an entire expression, and over here, what's going on is it's showing you why A, the inverse of A, and the inverse of b is different from the inverse of a and b. And the reason it's different is because I would substitute the values in before I perform the AND operation. Over here, I had to solve what's under it before, I would have to, solve what was under it and then inverse the result. So when you have an expression under not logic, the not above it just means that you would inverse whatever the result is. Okay, over here you have x, or the inverse of 1. This would be 0. 0 is insignificant when dealing with OR logic. Because of that, you have x. Okay, now over here, this is all using OR operators. Now what you can do is just take away the parentheses. However, when dealing with not logic, you have to keep A or B have to be both under the same not. So the result of this would be A or B, not C. It also is important that you take off the parentheses in your final result because it's simplified more. It's using less stuff. You want to make your answer as clear as possible. Now down here, the inverse of 0 is 1. 1 is insignificant when dealing with AND logic. Because of that, you just have x and y. And that's as simplified as you can get it. Down here, if I were to put a 1 right here, the value over here would get inverted and it would become a 0, which would make the whole entire equation false. If I were to put a 0 here, the value here would get inverted, and again this value would be 0, making the entire equation false. Because of that, this part would be false with B, and then again the entire equation false, which would be your solution. Okay, this is XOR logic. The X in XOR logic stands for exclusive, and this is just OR being used exclusively. Last time with OR logic, I said that it's OR logic because it includes the idea that it can be both values. However, XOR logic excludes it, meaning that a true value and a true value equals false. This right here is the only difference between OR logic and XOR logic. When you have chains or expressions that only deal with XOR logic, all the variable, not all the variables, but if you were to count up all the false and true values, the amount of true values must be an odd number for the entire equation to be equivalent to true. If you have the same number of false values and true values, the entire equation equals false. Okay, any variable XOR 1 is equivalent to the inverse of the variable, and you can sort of understand why if you just plug in numbers. If I were to plug in 1 for A and that were XORed 1, it would be false, because again, if you look at these truth tables, that would be 1 and 1, and this is exclusive OR, so it would be false, which would be the inverse of the variable we started off with, which was 1. Oops. Okay. I went back. Okay, sorry. And then any variable XORed 0 is just equivalent to the variable. Okay, down here some more practice. Okay, remember order of operations, not the order of operations, but the commutative rules do apply. So x XORed the inverse of x, that would be true if I put in 1, and this would be 0. Yeah, this would be 0, making that part of the equation true. Any true value, XORed a true value, is false. And because of that, the entire equation is false. Okay, over here, the way I would do this is I would take a look at this, and XORed x, because again, the commutative law, the two variables are going to be the same, obviously. So when you XOR two true values, you get false and false equals false, proving that this is false. This over here, remember what I said about the amount of true and false values? This a could be true or false, we don't know. And because of that, you could have an even number, which would make the equation false. You could have it be 0, and that would give you an odd number, which this would be the only one, which would make the... Oh, no, sorry, I forgot to invert this first. You would have... Yeah, that's one thing you always want to do first when dealing with these equations. If you can, inverse all your variables. Okay, so you have an even number to start off with. If this were to be a 1, it would make the equation true. If it were false, it would make the equation false. So because of that, your final answer would just be A. Now over here, same thing again, just check the number of true values. It's even, so the entire equation is false. Okay, this page shows you the Boolean order of precedence. If you notice the examples I've been giving you, every single example has all been done using the same operator. You didn't have to worry about what comes first. The word precedence means priority. An operator with a higher priority is done first. So number 1, you would do your parentheses, brackets, braces. Number 2, all not logic. Number 3, and logic. And number 4, XOR logic, and then 5, or. Okay, these are examples that have multiple, all kinds of different operators in them. And when you're doing a Boolean expression like this, it's important to look at what's done first and to sort of group them up. If you see, I circled both sides of the XOR operator because I know this part is going to be done first, and this part over here is also going to be done first, and then both values are eventually going to be in XOR with each other. So for this side, any value in 0 is obviously just 0. Or 1, any value or 1 is just 1, which again you get 0 or 1, which is always going to be true. Now over here, this one looks tricky, but it is really simple, because if you plug in a 1 for A, this one equals 0. And yeah, and when you have AND logic and you get a 0, the entire equation would be 0. And because of that, you just replace all this with a 0, and when 0 is in OR logic, it becomes insignificant, so you would end up with just A or B. Now this over here, again, you want to group them up first. So you get that would be done first, then the 0, 1, this. And the way that this equation is, with the way I circled it, you're only using AND logic. And because the AND logic is what's going to be done last, you know that it's eventually going to get to a point where it's in AND with 0. And because of that, the entire equation is equivalent to 0 or a false value. This last one down here, you can actually solve this with everything I just taught you. However, it is very hard. You really have to think outside of the box in order to get this one. If you want to try it, again, pause the video and try it out. But I'm going to go over it right now. What I'm going to start out with first is both sides to what's in the parentheses. The only part, the only situation that's going to be true for this side right here is if A were to be 0 and B were to be true. The only thing that would make this part of the equation true is if B were to be 0 and A were to be true. Now it's not possible for one value to be both 0 and 1. Because of that, you know that only one is going to be true at a time. If you take a look at the truth tables to A and B, you have 1, 1, 1, 0, 0, 1, and then 0, 0. This would be true for this equation right here. This part would be true for this part of the equation. Now you know that it's either going to be one or the other, or it's going to be one of these other two right here and be false, because it's either this one or this one that makes the equation true. I'm going to write the results, and you'll notice that this is the exact same results you get with XOR logic. And because of that, I'm going to erase all these annotations real quick. If I were to rewrite the equation, you'd get A and A, or used exclusively with B, and or A and B. Now all this is going to be done first because of the AND operator, and all this is going to be done first. But if you look at this, this can be simplified even further, because if you look at what has to be true, A for sure has to be true in order for the result of this side of the equation to be true. In order for what's in the parentheses to be true, one value has to be true and the other value has to be false. If A has to be true, and in here A has to be true and B has to be false in order for A to be true, then you know that the only thing that works would be if A were true and B were to be false. And if A were to be true and B were to be false, then this equation right here, A and the inverse of B, that this right here is the same thing that makes this equation true. Both this and this is the only thing that makes them true. However, this uses less operators. That's why it's the simplified version of it. Now I'm going to write over the rest of the equation. Now, this right here, A is being used with and towards the inverse of B and B, saying A and the inverse of B or A and B is equivalent to just saying A and B or the inverse of B. The reason that is equivalent, try replacing it with like word values. Like if someone were to say, in order to play outside, you need to wash the car and do the dishes, or you need to wash the car and mow the lawn. Well, you could easily just say, you need to wash the car because that's what you need to do for sure to play outside, or you can either do the dishes and mow the lawn. Logically, they're the same. That's why I replaced them. Okay, and because you have B or its inverse, you know one of these values is going to be true. And if one value is true in OR logic, you can replace this whole entire thing with a true value. And because you end up with A or a true value, the true value is insignificant. It depends upon the result of A. Because of this, the final equation is equivalent to A. If you did not get this at first, don't worry, this is very hard. I'm only included this in this basic video to show you what's out there. I don't actually expect you to be able to do this at this point in time. Okay, the tutorial's over. If you have any questions or you would like a video going over more advanced stuff, please leave a comment below. Thanks for watching.